Hi, it's time for the next part in the power supply series. I've been designing this cute little power supply and I thought we'd take a look at the final schematic. Let's go! And if you remember the previous videos, here's the existing circuit we already had, which I breadboarded up, and we pretty much developed this from scratch. Now, the final schematic we're going to go through today is essentially exactly the same configuration as this, but I've gilded the lily a bit, added a few niceties, and put some system engineering into it, I guess you could say, and ta-da! Here it is. Here's the final schematic. Now, it might look a bit complicated. That's because I've put it all, sort of crammed it all onto an A4 sheet here. It's not terribly modular, but stick with me. We'll go through it and you'll see that it's not that hard at all. It's very simple. First of all, if you take away all the other circuitry there, you'll find that this circuitry in here is pretty much identical to our existing circuit here. So let's take a look at that part of it first, and the current shunt amplifier and resistor, which I've changed up here. But before we do that, let's just take a look at the thing from a block diagram level, shall we? This is exactly the same circuit we had before. I've added a microcontroller down here. It's an ATmega 168. It could be an ATmega 328 or whatever, any of those 28-pin ATmegas. It's going to be Arduino compatible because the software will be written in the Arduino software environment. I've added external ADC here, around here with some voltage followers, and an external DAC as well. Now, you know how I did the video on the pulse width modulation output and how you can control the output voltage and current with PWM? I was originally going to do that because most microcontrollers are only 10-bit resolution ADCs. So, I don't know, I decided to gild the lily a bit. I wanted a bit more resolution, so I'm using external 12-bit DAC and an external 12-bit ADC, which we'll go into later. Up here we've got LCD, because we've got to have an LCD display to display the voltage and current and all sorts of other stuff. It's an I2C one, we'll go into that. Some push button switches, rotary encoders down here, 2 of them, one for voltage, one for current. Decided not to use the more expensive 10-turn pots. Up here I've added a 5-volt USB output connector on the front panel with some iPod kind of compatible things in there, so it can tell an iPod that it's a genuine charger, just so that you can power 5-volt USB devices directly. There's a couple of voltage regulators up here, and here I've really gilded the lily here. I've added what is essentially one of my microcurrent devices into the design here. So I think this is probably one of the first power supplies, bench power supplies on the market that I'm aware of anyway, that can measure down to microamps output current. So it can do a massive range from anywhere from a couple of microamps all the way up to a couple of amps with full resolution and full accuracy. So that's a little nicety I've gone to the trouble to add there. We'll take a look at that, but that's the basic block diagram. In the previous design, we used a very crude differential amplifier here for the current shunt, and that's not very accurate at high resolution stuff, 10 or 12 bits, which we're trying to do here. It'd be okay for 8-bit or something like that. But so I've decided to add a Maxim Max 4080F high side current sense amplifier. It's specifically designed for the task, and it does a really nice job. It's only $1 or $1.50 or something like that. So it's, you know, it's a reasonable price, but it's very accurate and does a really good job. The current shunt resistor here, I've actually made up. When I've laid out my board, I've put in 10 half watt resistor footprints in there, so that you can basically get better than your 1% typical tolerance, because it's quite difficult to get an accurate precision current shunt resistor like 0.5% or 0.1% or 0.2 or something. It's very difficult to actually get those. They're very difficult and expensive to source. So I've put 10 resistors in parallel. So hopefully, if you see my previous videos on the Gaussian resistor response, we should get better than the typical 1% resistors we're using, the tolerance there. Now, because we've got an intelligent controller over here, we don't really technically need a high precision accurate resistors in all of this power supply design, because we can calibrate the thing and compensate for that in software, but that's just not nice. I didn't want to have to do that, so I've made this overall design fairly high precision. So I've used a 0.1% high side current sense amplifier here. I've used 0.1% resistors elsewhere in the circuit down here, as we'll see. And the current sense resistor, well, we'll see what we can get when we actually build the thing up, but I'm going to try and get it as accurate as possible. Now you'll notice on my schematics that I've added these notes in various places here, and I love doing that sort of thing because it just put formulas and things like that in little boxes next to the actual pin that you're actually talking about, and it just helps explain the schematic, and when you come and look at it later, all the formulas are there and you don't have to do the calculations. It's all done, and little notes and things. You know, you might add a star ground over here, so you put little notes and current values and things like that. That's just a nice touch to add to any schematic that you're actually doing. So we're using a Maxim 4080F high side current sense amplifier, and that's got a fixed gain of 5. It's basically a differential amplifier, so it measures the differential voltage across a high side current shunt resistor we've got here, and it multiplies by 5, and it gives you a direct voltage output referenced to ground, and that's all it is. Very simple device, and this is quite a precise one, and it's 0.1%. So with a gain of 5, we can do various calculations up here for various current shunt resistor values. Now, I'll just mention that I'm actually using a 2.048 voltage reference here. It happens to be an ISL 21070, but it can be any one on the market really. It's not too bad. It's 30 ppm plus minus 0.25%. Now, why I'm using 2.048 volts instead of the more traditional 2.5 volt voltage reference is because then the values that we're going to get out of our analog to digital converter are going to be spot on. We don't have to fudge them or do anything like that. Now, I'll give you an example of that. Let's say we use a 2.5 volt voltage reference, okay? And we're using a 12-bit analog to digital converter. There's going to be 2 to the power of 12, or 4,096 different steps in that analog to digital converter. Now, if we divide our 2.5 volts maximum input to our analog to digital converter, because we're using the 2.5 volt voltage reference, divide that by 4,096 steps, you end up with some weird ass value here of 610 or thereabouts microvolts per bit resolution on your analog to digital converter. And that's hopeless. You know, if you feed in 100, if you're measuring 100 bits out or something, that represents a voltage of 61.035 millivolts. It's not a nice round number. It sucks. So and you have to compensate for that in software. You've got to actually do some math in software. It's not that bad, but there's a reason they make these voltage references which correspond to like a power of 2 to match your analog to digital converter. In this case 2.048 volts, but you can get 4.096 volt voltage reference, but 2.04 volts is more common. So we're going to use that. So look what happens if you're using 2.048 volts, okay, on a maximum ADC value, and you divide that by your 4,096 bits, bingo, you've got a nice round number of 500 microvolts per bit. And if you have a look up here of when you translate this into your current shunt values, you end up with a very nice round 500 microamps per bit resolution, or if you use different values, you can have 1 milliamp per bit resolution precisely from the output of your analog to digital converter. And that works out really nice in your software. I love it, and that's why I've used it. If we take a look at our current shunt resistor R here, let's take a value of 2 ohms. If you put 10 in parallel, you're going to get 0.2 ohms current shunt resistor. Now I've put up here for a gain of 5 in this Max 4080. Remember, it's built in, gain of 5. You can get different versions, a gain of 20 or I think a gain of 60, but we're going to use a gain of 5, and I'll tell you why in a minute. And that will give us, because it's a gain of 5, okay, 0.2 ohms, let's say an amp through it is 0.2 volts multiplied by a gain of 5 is 1 volt. So you're going to get out of your current sense amplifier here, you're going to get out 1 volt per amp output. And of course, that will give you a range, because you're using a reference voltage on your analog to digital converter. It's going to give you a range, a usable, measurable range of 0 to 2.048 amps. And that translates to 500 microamps per bit resolution. And you can go through, let's say you wanted to use a 3 amp version of this LT3080, the LT3083, then you could say set it for a 4 amp current range, and you still get an excellent resolution of 1 millivolt per bit. Awesome. And because you've used 10 resistors in parallel like this, say at half a watt each, or you might have a 1 watt resistor in there, then you might have 5 watts or 10 watts dissipation capability in your current shunt resistor there, and that's plenty. So this current shunt resistor isn't going to heat up at all, so you can use fairly low grade ones, and they're going to work quite well. They're not going to change much with temperature because they don't heat up much. Let's take the example of the 2 ohm resistor here. If we've got 2 amps flowing through it, I squared R, 2 squared is 4, and times 0.2 ohms, we're only going to dissipate 0.8 watts in all of those resistors. And if we've got 5 watts total capability or 10 watts, not a problem whatsoever. It's not going to heat up much at all. Now, of course, the value of your current shunt resistor is going to determine how much voltage drop you get across there, and depending on your input voltage over here, depending on what you power it from, that may be an issue. In this case, if we use 0.1 ohms, then we're only, well, in either of these two cases up here, we're only talking about a 0.4 volts maximum drop, which really isn't that bad at all. And you don't want to make it too low and use like a gain of 20 here or gain of 60, because then you can start getting right down into the noise and you can get errors and issues like that. So you really don't want to go there. You want to you want to get as maximum voltage drop across your current shunt resistor as you can tolerate, and the lowest gain here, so you minimize your errors. So how much error can you tolerate in this amplifier here? What's the minimum? Well, it depends on your specs and what you're willing to, whether or not you're willing to compensate for it in software, which I don't really want to do. I want to try and get the maximum possible absolute accuracy out of this thing. So the input offset error of this amplifier is going to matter. So you can't make this resistor, shunt resistor, arbitrarily small, because then the voltage drop's going to be so small it's going to be swamped by the input offset voltage of this op amp, of this amplifier here. So what's the minimum that we can tolerate? Well, it's a basic rule of thumb is that, well, you don't want it to be any more than 1 bit resolution on your analog to digital converter. You want to be able to measure accurately down to your last bit. Why not? So in this case, we've got 500 microamps per bit. So 500 microamps is the minimum we can measure. So if we do 500 microamps here times our 0.2 ohm resistor there, we're basically going to get 100 microvolts drop across this resistor here. So that's the minimum that we're going to get, 100 microvolts. So let's go over to our data sheet here for our max 4080 device, and what's its input offset voltage? What a coincidence! It's 100 microvolts. Typical, you could go into there, but it's going to be 100 microvolts input offset voltage. So as you can see, the max 4080 is almost ideal for this. Its input offset voltage is exactly the same as our minimum voltage on our input here. That's pretty good. I mean, ideally, you know, if you're designing a really high precision thing, you'd want it to be maybe an order of magnitude low, order of magnitude lower or something like that. But in this case, perfect, good enough. We're happy for a 1-bit error there. And of course, the input offset voltage is just that. It's relative to the input. So this amplifier has a gain. So the actual output the error you're going to get on the output is the input offset voltage times 5, which is 500 microvolts error on the output. But because it scales up 5, we're still only talking about 1 bit error there caused by our input offset voltage. Beautiful. And as I said, you just can't make that resistor arbitrarily low, because not only is there input offset voltages, but then you get noise and things like that causing issues. So there you go. That's almost perfect, that device. And just to get rid of any noise, I've added just a little RC low pass filter there, which then goes down into our existing circuit, which we've seen before, our constant current comparator down the bottom here. And not only that, if you look at the net name there, it also goes over to our analog to digital converter over here, one of the channels. There it is, ADC I out. Now, speaking of the ADC, we've used a 4-channel one here, and so it's going to measure, not only does it measure the output current via here, it also measures the output current from this microamp circuit over here. So I can measure the current 2 different ways, either in series with the output like that. Well, they're both in series with the output. I'll explain this one later. But it measures the output from the microcurrent, and it can also measure the output voltage, which we'll take a look at there, and also the ADC input, the voltage input as well, coming from your source. So then your software is able to determine whether or not it's got adequate voltage and whether or not this regulator is going to actually drop out. So our 2.048 voltage reference here goes into the DAC over here, the 12-bit DAC, and it also goes over to our 12-bit analog to digital converter here, and both of those are devices from Microchip. This is the DAC is an MCP 4922 and the ADC is an MCP 3204. So why did I choose this specific analog to digital converter and DAC? Well, let's find out. Let's go and do a parametric search in DigiKey here. Let's search for ADC, and we'll go down here to analog to digital converters, ADC. There we go, almost 13,000 of them. Can you believe it? And here we go. Here's our parameters. We want a 12-bit converter only. There's no point searching for all the others, so let's drill that down. Bingo, we've still got 4,434 different converters. Well, because this is a kit, we only want through hole, so we'll select through hole over here, and we apply the filter. And bingo, we're down to 439 ADCs. So from these particular manufacturers, Microchip, I like them, National, Texas, all the biggies are there, linear analog devices. But let's sort by price, because, well, really, I do care about price. So let's search for that. Let's say we're going to make 100 kits. Let's sort by price based on 100, and bingo, what comes up first? Not terribly surprising, Microchip. They make pretty cheap analog parts. People mostly know them for their PIC microcontrollers and stuff like that, but they make some pretty cheap analog stuff. I'm finding I'm using more and more of them lately. So basically, let's have a look at the number of converters. It's only got one. Bang, not too happy with that. We want, basically, we want something with at least 4 channels in there. So let's select that. Hey, what's going on? No, I'm pretty sure there's a Microchip one in there. So something's happened to that DigiKey search. I don't know what's gone wrong there. Something horrible. But here we go. Look, DigiKey's got it wrong. Here's my converter. It's a 4-channel. It's only got one number of converters. 1. Wah. Fail. Okay, so much for that. But there you go. The cheapest devices there. These are single channel, dual channel, and the cheapest device, 4-channel ADC we can get is a Microchip MCP 3204. And bingo, that's the one I used, purely because it was the cheapest in quantity. It was $2.40 in 100 of quantity, which is, expensive, but it is a 12-bit converter. The next nearest brand is Analog Device, Texas Instruments ADS7822, but that won't be a 4-channel in an 8-pin package. So really, there's no competition. The prices start going up and up and up. So that's why I chose the Microchip, and I did exactly the same thing for the DAC, and the matching Microchip DAC, unsurprisingly, I guess, came up as the cheapest again. So that's why I used them. That's parametric search. And if you're wondering why I just didn't use a microcontroller with a 12-bit analog to digital converter and PWM in it? Well, let's take a look. I've gone through and selected all the DIP devices here. You can't select through hole, so I just want DIP microcontrollers. I'm searching through the 32,000 microcontrollers available from DigiKey, any brand, any manufacturer. So let's take a look over here. ADC at 12 bits. 12 bits, 12 bits. It gets a bit tedious. You have to go through and select your 12-bit ones in here. But if we do that, and then if we go through and select just the ones in here with 12-bit ADCs, let's not worry about the PWM at the moment because that's harder to find. But let's just, as a first pass, find ones with 12-bit analog to digital converters. What do we got? We've got Freescale and we've got Microchip. That's it. So all you Atmel fanboys out there, don't come running why I didn't use some Atmel thing or if you're a TI fanboy, why I didn't use those, because they're not available with a 12-bit ADC in a DIP package. So there you go. And if we go along here and we probably search for, say, the best price over here, let's 100 of quantity. Let's have a look. It happens to be the Freescale, the HCS 08. That's going to be a tiny little device. That's only a 16-pin DIP, not enough pins, 28-pin DIP. May or may not be enough. You know, it's just, I don't know. And then you get into the PIC devices here, and there are quite a few PIC devices available with 12-bit analog to digital converters. But if you want one with a decent number of pins, and then you'd have to go through and look at the ones that actually have a 12-bit capable pulse width modulation output, it just gets trickier and trickier. And, well, it was just all too hard. So I just simply decided to use an external ADC and DAC. And generally, anyway, you're going to get better performance with an external ADC and DAC. The ones built into microcontrollers aren't that great. So when you start trying to push 12 bits inside a microcontroller, you know, you're probably better off going to external. 10. That's why most of them only have 10 bits, because that's generally all they're good up to. Now you see that I've got a couple of voltage buffers down here driving the ADC like this. Now, there's a reason I've actually got that, is because when you've got a successive approximation ADC like this, you can't have an arbitrarily high input impedance. So in this case, ADC V out is coming from over here. Look at these 10K resistors, okay? We've got a relatively high input impedance driving this analog to digital converter, and this has sample and holds in here, and it can cause you all sorts of problems. So it's good practice to actually buffer that so it provides a low impedance drive to your analog to digital converter. These ones here don't need it because it's coming directly from the output of the op amp here through a little low pass filter of 330 ohms here. Not a problem, that's low enough not to cause an issue. And the other comes from the ADC I out, which is the current we looked at before, and once again it's 330 ohms, low enough not to cause an issue. And as always, read the data sheet. Here's the ADC, the MCP3204, which is the 4-channel version. Also available in 8-channel version. It actually warns you about high input impedances. And here's the equivalent circuit of the analog to digital converter. And as you can see, it's got an inbuilt sampling switch here with an internal series resistance of 1K, and then it's got a 20 picofarad sampling capacitor on here. And basically, your input impedance, which I just talked about over here, here's your input pin. So this is all inside of the analog to digital converter chip. So your external impedance here will actually affect the time that this capacitor takes to charge up. So that's charge up to the value. And if you've got a 12-bit converter, it's got to get very close to the nominal value not to introduce any additional errors into your analog to digital converter. And if you take a look down here, they actually provide you a graph here. So that actually shows you the input resistance in ohms, 10K here, 1K here, down to 100 ohms down here, and the maximum clock rate in megahertz at different voltages. And as you can see, if you're operating at a low voltage, we're operating at 3.3 volts. So it's going to be like in there somewhere. There's going to be another curve which goes in there and down like that. And as you can see, if you've got a 10K input impedance, it's useless. You can't get a 0.1% least significant bit deviation on this thing. So the input impedance matters. In practice, we may not need these op amps down here, and if we don't need them, well, we can just not insert it and then just short out pins 2 and 3 and 5 and 6 there. Not a problem, but good practice to put it in if you need it based on your input resistance, because that can affect your maximum sampling rate. And by the way, it's not just specific to this analog to digital converter either. If you use the one inside your microcontroller, you would have the same issue. Just beware. Now, I've actually used a really cheap garden variety op amp here. It's an NMJ 14558. It's a variation on the very common 4558 op amp. And this one has a nominal value, not a maximum value, but nominal of 500 microvolts input offset voltage. So that should be good enough for our circuit, but as always, it's a standard pin out. If we need to put really better precision op amps in there, we just drop them in. And as for our 12-bit DAC over here, well, it's pretty darn boring. There's some digital input lines here. It's an SPI, so we've got a clock, a chip select, and data input, a voltage reference input, bypass cap, and it just outputs 2 different voltages. It's a dual channel 12-bit DAC, this one. It's quite nice. Well, for the price, it's really cheap. And so that just generates our VSET and ISET exactly as we would if we hooked a pot onto here like we've seen in the previous videos, or we use a pulse width modulation output from our digital or from our microcontroller here. We could also drive it. But a nice good 12-bit resolution DAC, that gives us some great resolution on the output. And as for our current resolution, well, we've already looked at that. We can actually set the current limit in steps of 500 microamps. Brilliant, over the whole range of 500 microamps to 2 amps. Fantastic. That's the advantage you get with the 12-bit analog 12-bit DAC. If we used a 10-bit DAC, you'd be looking at 2 milliamps per bit. Not as good, but still, you know, might be certainly adequate. So I've just gilded the lily here. You could have just used the microcontroller for sure. Depends on your requirements. Now, as for our voltage output, well, our DAC is going to give out 0 to 2.048 volts, because that's our voltage reference coming in here. So 0 to 2.048 volts, I've put in a gain of 5 here in this amplifier set by these 2 resistors here. Exactly the same circuit you've seen before. The tap actually comes from here, so it compensates for these series resistances here. But that circuit has a gain of 5. So once again, I've put an engineering node in there, and there it is. Gain equals 5, 0 to 2.48 volts input, which gives a 0 to 10.24 volts output with 2.5 millivolt resolution for our 12-bit analog to digital converter. So we can set our output, our voltage output up here on the supply in steps of 2.5 millivolts. Awesome. And of course, if you used a 10-bit DAC or a 10-bit PWM in your microcontroller, you would get a 10 millivolt resolution output. Once again, that's still adequate for most purposes. I'm just gilding the lily. Some of you might be asking, why have I put 2 resistors in parallel here and 2 resistors in series? Well, if you'll note, they're all 10K. I've tried to basically optimize my design to reuse existing values on my sheets here. So I've got 10K up there, 0.1%, because these resistors are fairly expensive because they're 0.1% tolerance. So I've just used them. It's better. I think it's better to use them and reduce more of them and reduce your bill of materials than it is to have all these different values. And over here, which we'll look at later, I've also used 10K there as well and 10K here. So I bought, you can buy a whole bunch of those so you can consolidate your bill of materials and you only have to buy the one item. That's not bad. So I've done that up here, like for this last time. You'll notice that I set my current fixed current output here, the LM334 to 1 milliamp, but that required an oddball value resistor here I'm not using elsewhere on my circuit. So I decided to use 100 ohm. I am using elsewhere in the circuit, and it's still good enough, 677 micro amps, good enough for a minimum load on our LT3080. Component consolidation is one of those steps you should do in any good design. So you'll see not only the resistors I've done that, but also elsewhere on the circuit I've done that for the capacitors as well. If I needed 4.7 microfarads and I don't use it anywhere else, well, but I've used 10 microfarads somewhere else, well, I'm going to use a 10 microfarad in there instead of the 4.7. And for output protection, I've got a big, nice 5 amp reverse Schottky diode there. Now, this is the output. I'm going to have a load switch external to the board. It's not actually mounted on the board, and that's why it's not shown here. And you'll note that this is my sense line that senses the output voltage goes back to the analog to digital converter down here. This net here goes down to the ADC. Now, the reason I'm doing that is because some people like to have the sense line directly on the output so that it still reads the voltage when the load switch is open. Others prefer it the other way around. They like to know what the output voltage is going to be before they, or what the output voltage actually is, regardless of the load switch position. So this, just having a separate sense line, gives people the flexibility to wire it up any way they like. And once again, I've just got some voltage divider resistors here, and that will give me a certain voltage into my analog to digital converter scaled down to meet my 2.04 volt voltage reference. And more than that, it is precisely, the voltage here is precisely 1/5 of the output voltage. And coincidentally, remember, I had a ×5 gain over here. So once again, that scales perfectly. If my max output voltage is 10.24 volts divided by 5, the max input to my ADC is going to be 2.048 volts, or the output voltage divided by 5. So it's perfect. I'm using the full maximum range of my analog to digital converter to measure my output, and that's what you want. You don't want to piss away any bits. Now, as for the current limit LED indicator over here, you know how I used this convoluted op amp before. I just wanted to show you that you could actually do that as a spare op amp, but that's not the nicest way. It's better to actually use a second transistor here and drive it direct, and that's exactly what I've done on the circuit here. Here's my current limit comparator down here, and as well as driving the set pin, as per normal, it also drives a second transistor here, because we've already used them, same type, very cheap, you already got them, and that current limit goes into your microcontroller over here. It doesn't go directly to a LED. I decided to put input pin, and then the software can do intelligent stuff with the LED. It can blink it and do all sorts of things depending on various modes. So there you go, and you don't need a pull-up resistor on there, because you can program a pull-up resistor directly on your microcontroller here. And you'll notice the same with the optical rotary encoders. They've got two outputs here. They go directly into the microcontroller. Normally they need pull-up resistors on there, but you can do it inside the micro. No problems. Save a couple of resistors, save some board space. Now let's take a look at this, effectively a microcurrent circuit here, which allows us to measure if this lab power supply is powering your little microcontroller circuit and goes into sleep mode, well, you don't have to use your multimeter. This power supply will be able to actually measure low values. Not as good as the microcurrent. It only goes down to a maximum of 2.5 microamps per bit, as we'll go into. But still, I don't know any other power supply that can measure the output current down to 2.5 microamps. And the way it does that is that basically this circuit doesn't operate all the time. This circuit will only effectively be in use when you want to measure low values, and your microcontroller knows that the values are very low. It can switch this circuit in, and it does that with this MOSFET here. It can switch on this and effectively insert another load, because our output voltage here's our output voltage here, but the ground, here's our output, our negative output terminal. And instead of going directly to ground, it goes through a current shunt resistor, here what's called a low side, as opposed to the high side current shunt resistor we have up here. We have an additional low side one, and normally I don't like doing that, because then it introduces an offset voltage error here from ground, and depending upon your output current. That's why at very high output currents, we don't want to go through this resistor here. We want to shunt that, excuse the pun, we want to shunt that through a much lower value MOSFET here so we don't get any errors introduced on our low side. It's going to be effectively ground. So let's say we wanted to only tolerate 1 bit resolution error on this output. What value do we need? Well, our output voltage is, maximum output voltage is 10.25 volts, 2.4 volts, sorry, divided by 4096. We've got a 12-bit converter, so 2.5 millivolts. So basically, our ADC down here can measure our output voltage to 2.5 millivolts resolution. So it'd be nice if this circuit here only dropped 2.5 millivolts or 1 bit or less. So pretty much we want 2.5 millivolts maximum drop across this MOSFET here when it's switched on and all this circuit is disconnected on our high current range. Our maximum resistance there is going to be 2.5 millivolts divided by the 2 amps maximum current there, 1.25 milliohms. So our FET there needs to get 1 bit error is going to need 1.25 milliohms. So that's actually a very low value for a MOSFET. If you actually want to meet that, you need a really, really beefy MOSFET. I've decided to use one of these. It's cheap, readily available in a nice package. I like it. It's going to be near enough. It's got a rated maximum RDS on, or a maximum resistance of 8.4 milliohms, but that's going to be at the maximum current. It's going to be better than that at the lower current and at higher VGSs as well, or higher gate source voltages. So in any case, that MOSFET should give us a very insignificant error at our maximum range of 2 amps. So as I said, the software is capable of switching this MOSFET on, and to do that, I've actually, to get a higher gate source voltage, I've actually used, rather than drive it directly from the microcontroller, which would only be a 0 to 3.3 volt output, that's not really good enough for this MOSFET. I really want it a nice high value, so I'm going to tie it to V plus here, and I'm going to use an external transistor to turn it off and on. So the gate voltage is going to go between 0 and V plus, which is our input, all the way over here. So we're getting a nice high gate source voltage, because the higher the gate source voltage, the lower the turn-on resistance for this MOSFET. So you want it as low as possible. And during that 2 amp range, this circuit isn't used at all. It's still measuring, it's trying to measure something, but we don't read it at all. The micro doesn't read it. We're doing our measurement based on this high side and current shunt resistor. So we've effectively got 2 different current measurement ranges. So let's have a look at the low value current measurement when this circuit is active. Now what we've got here is we've got 4 resistors here, 1 ohm. They're in a series parallel combination, giving a total shunt resistor here, low side shunt resistor value of 1 ohm. Now the reason I'm using 4 like that is, well, not only to get a little bit extra accuracy like we did with the high side current shunt resistor, but a bit of margin for error in case the software selects the wrong range when there's actually a high output current. So in this case, let's say it was 2 amps maximum like that, then in theory, if the software accidentally turned this transistor off instead of on, then all that current would try and flow through, would flow through these resistors here, and we would get a power dissipation in those resistors of 4 watts. So really, you know, if you put a tiny little resistor, single resistor in there, you might burn it out accidentally. You don't want that to happen. So a couple of extra resistors, it's, you know, it's going to survive anyway. It's still not going to be great. It's going to be very, very hot, but it'll at least survive and it won't blow those resistors. So if we've got a 1 ohm current shunt resistor here and 1 milliamp flows through there, we're going to have 1 millivolt across here. This op amp, the max 4238 you've seen in my microcurrent, it's exactly the same. It's got a gain set by these 2 resistors here of 200. It's quite a high gain, and so if we've got 1 millivolt drop across the shunt resistor, we'll get 0.2 volts output. So my little engineering note here says at a gain of 200, the V out equals 0.2 volts per milliamp flowing through here. And from that we can determine our maximum range, because our ADC down here, remember, it's only 2.048 volts maximum, so it can only tolerate that voltage, or it can only read that voltage maximum. So we can have 10 times that, or roughly 10 milliamps, or if you want to round it off, 10.24 milliamps maximum is what this circuit is capable of measuring. So the microcontroller, when it measures over here on this shunt resistor that the current drops below 10 milliamps, or you can do it under manual control with one of the switches here, it can automatically, if it wants, switch on, disconnect this MOSFET, and then start reading from this circuit over here. So if let's say your circuit's powering your microcontroller, but this power supply is powering your microcontroller circuit, it's just gone into sleep mode, the software of this power supply can detect that, and it can switch on this circuit and measure that sleep current accurately. I think that's brilliant. Why can't all power supplies have a feature like that? So just like the high side current sense amplifier, what is the maximum input offset voltage we can tolerate here before we start getting errors? Well, if our maximum output is 2.048 volts, okay, we divide that by our 4096, we're getting 500 microvolts is our minimum on the output here. So we're going to read 500 microvolts per bit, 1-bit resolution here, but we've got a gain of 200. So let's divide that by 200, okay, and it can tolerate, and that translates to 2.5 microvolts is our minimum per bit value across here. And of course, the only way that you're going to get an input offset, a voltage error pretty much of down in the order of 2.5 microvolts, as you've seen in my microcurrent, is to use a chopper amplifier, an auto zero-in amplifier, which is exactly what the Max 4238 is. And what is its value? An ultra-low 0.1 volts microvolt offset voltage, more than an order of magnitude more than what we need. But that's typical, but its maximum at ambient temperature, or even over the full temperature range, is our 2.5 microvolts. So over the full temperature range, we're only going to get 1 bit error. Fantastic. More than what we need. A little bit overkill, but hell, I already used that in the microcurrent, so I'm going to use it here again. Now, because I wanted to make this design into a kit, I wanted all the components to be through-hole, and I tried as hard as I could to make everything through-hole, but unfortunately, the Max 4238 is only in an SO8 package, and likewise the Max 4080 is only in an SO8 package, and the voltage reference, although I can get ones in like a TO92 package, they're cheaper and more readily available, especially in the 2.048 volt version, in a SOT23. So they're the only 3 surface mount parts on the entire design. Everything else is through hole, and I pretty much optimized, I chose parts based on through hole availability. There were maybe 1 or 2 others on the market for the current sense amp, but they weren't quite right and didn't have the right gain, and it didn't work out the values, and it just wasn't nice. So I was pretty much forced to use an SO8 there and pretty much an SO8 over here. And because I've used the chip before, oh well, you can't have everything. You have to, if you go and build this thing up, you're going to have to solder a couple of SO8 packages. Sorry. And I've got a little Maxim MCP 1700 3.3 volt voltage regulator. They're quite nice devices. They're actually got very high, very close output tolerance of 1% or less, or 0.5%. They're really quite neat. You can actually use those almost as a voltage reference at an ambient temperature. I think I've mentioned that before, but anyway, I've got a standard LM7805 to give our 5 volts out from our USB output connector over here. And because I've this is the heatsink I'm actually using. It's from Altronics here in Australia. I don't think you can buy it anywhere else. I think it is specific to them. It's a PCB mount one. It's got PCB pins. It's upside down there because it was in my breadboard before, but it's got an extra hole here so I can mount both devices on the same heatsink. But just be careful. You don't want to put them directly on there like that, because then you'll short out the tabs which are connected through to the center pin, and in this case it'd be ground and output, which you'd be shorting. So if you put this package here on, if you put both these packages on the same heatsink, you'd actually be shorting the output of your LT3080. So, whoops, you don't want that. Make sure you put some mica washers or some seal pad in there to isolate them from the heatsink. Now, as you'll see down here with the micro, I've actually used every available pin, every single one of them, and I probably goofed up here. I think I'm actually going to change it because I thought I could get away with using the 8 MHz internal oscillator in here, and it'd be good enough to do my external serial RS-232 comms. But to do RS-232, as a rule of thumb, you need a 1% tolerance frequency error or better, and the oscillator in this thing can be trimmed to 1% or better in software. You can actually software trim it, but it's not as good as the PIC one. I've done this on the PIC before, and they come factory trimmed to 1% or better. So out of the factory, over temperature, you can actually fairly reliably do RS-232, but I don't think that's the case for the Atmel. So probably going to have to use, I'm going to have to free up these two pins down the bottom and put a oscillator on there, the external 8 MHz oscillator on there, or 16, or whatever you want to use, which is Arduino compatible. You can use either and change it, but I'll probably use a ceramic resonator there at 8 MHz. So I've got to free up 2 extra lines here so I can get precision RS-232 serial comms out of here. I think it's just, you know, it's good practice. One of those ceramic resonators, you'll get, you know, easily get 0.5% tolerance on those, so more than good enough for RS-232. Now, the reason I've added a separate serial port here, it'll be a separate board, because really I want it to be able to do a whole bunch of things, be it just a standard, you know, 9-pin RS-232, you know, have an RS-232 chip to a 9-pin serial interface, or you can have electrically isolated, because a power supply, you can get major problems if your connectors on the back are referenced to the computer, which is referenced to mains earth. That can be a big problem. So electrical isolation can be a big issue. So you can build a separate board with a USB to an isolated USB interface to RS-232 if you wanted to, or you could use one of those XB wireless boards or something like that. So this could be a wireless controlled power supply. That'd be awesome. There's no reason why you can't do that at all. That'd be fantastic. So to free up these pins, basically my DAC up here and my ADC over here, they're both SPI input devices, and because I had enough pins available, I just drove them separately. But what I'm going to have to do is actually combine the clock pin on both. So instead of having a separate clock pin coming from the micro, I'll have the same clock pin and I'll have the same data input pin as well. They can be shared, and I'll just have a separate chip select pin for each, separate chip select for the ADC and DAC, and that should do it. Bingo! I free up 2 pins so I can put the ceramic resonator, and we're all sweet for our RS-232 and Arduino compatibility. And I've got the external AVR ISP interface here, so you can program the chip in circuit and download your hex code to it. No problems. For the LCD display up here, I've chosen a New Haven display. I rather like them, and they're one of the LCD manufacturers that I like. Their displays are quite neat. And what it is it's an I2C interface. There it is, SCL and SDA. That requires less pins on your microcontroller. So I freed up pins here. Rather than using a standard parallel or 4-bit interface one, I can get away with just, well, 3 lines actually. There's an LCD reset line as well, but that wasn't the only reason. Here it is. It just so happened that this LCD fits nicely into the case that I'm using. It was exactly the right dimensions, and it's a 20 character by 2 line, because I figured 16 by 2 probably wouldn't be able to give the status displays that I actually wanted. So it's a 20 character by 2 line display, I2C compatible input. It's only about $8 or $10 or something. It is the most expensive component in the whole in this entire power supply project, but you've got to have a decent display. This is actually an RGB backlight one. I didn't want that, but that's the only one that they had in stock for a couple of months, so I'm not using the backlight. It'll just be standard. But there you go. I pretty much, a lot of my design decisions for this entire project were actually built around the case, the actual case I'm going to build this in, and another aspect I haven't talked about the project, which you'll find out about in another video. And so I'll talk about that next time. I think how I system engineered this thing to fit into this case, because that's really a very important decision, and that drove a lot of the design requirements in terms of how many switches I used to fit on my front panel, whether or not I had room for a USB output connector, the type of heatsink I used, the maximum power dissipation, all sorts of stuff, the room I had for the LCD, for the controls, how big I could make those, the knobs, how big they could be, whether or not I could use 10-turn pots, and everything just sort of, was pretty much revolved around the case I'm using. So this video's been long enough. I'll have to make that a separate video, and I've already designed the PCB for this thing. I've got some time-lapse video of me doing that. So there'll be a couple of more videos coming up. In fact, probably more than 2 or 3 coming up to finish off this power supply project. So thanks. See you next time.